Hi class, we are now on beginning chapter 3. We're going to be looking at atoms and inside the atoms. So once we get started here, atoms. Everything we see, we touch, we taste, etc. is all made of matter. And all matter is composed of elements from the periodic table. So at this time, there are 118 known elements and only 98 occurring naturally. So what does that mean? That means that the rest of them have been created in a lab, synthesized is the word, in a lab, and some for only seconds, but they've existed. And so because they've existed, they are on the periodic table, and they are the bottom ones. There's some interesting how these have been named, and we'll start covering names later on. So elements are made up of atoms. The atom is the smallest unit. So every element is made up of its own atoms. For instance, iron is made up of iron atoms. Cobalt is made up of cobalt atoms, and etc. The atom is the smallest unit of matter. So remember that each element is made up of one type of atom, and it gives one set of an element's atoms, gives it its unique property. And if we take, for instance, I mentioned this before, if we take a mountain of iron atoms, we take them away till we get to one final atom. That is the smallest identifying property of that of iron element. Once we start, there's nothing more. Once we go into breaking it open, we're now looking at subatomic particles. So when we're talking about the properties that go with iron, that is it. That's the last part of it. So in 400 BCE, I don't know how to say these names right. Democritus, I know that's not right. The Greek philosopher, he lived around 400 BCE. He derived that by cutting a substance in half, you have two pieces of the same substance. And if you keep cutting in half, you will get to a point that you cannot cut in half anymore and still have the substance. And that's exactly how you think of an atom. Once you cut an atom, you are no longer dealing with the properties, for instance, like iron. So you can't cut anymore. You can cut in, but you're no longer dealing with that element's properties and substance. So that's the same general idea. You're at the end of the substance, which is an atom, and it's named atomos, which means indivisible. So now we're going to look at the law of conservation. This is, again, I'm not great with these names. And Antoine, I'm sure somebody will correct me on that. Lavoisier, I will tell you that it's interesting because I walked in one night in my house and Jeopardy was on and they had a chemistry column. And he was one of the answers. I think he was the Daily Double. And I didn't know how he died. And he was killed, I believe it's during that French Revolution time, because he was killed on the guillotine at the age of 50, if I was right. I probably should look at that math, those years here. But around that time. Didn't know that. So I thought that was really interesting. Anyways, let's get started with this. So he played a huge role in science. He observed while conducting, he did many things, but this is one of the big ones, that we're going to focus on for this section. He observed while conducting chemical reactions that the mass, his starting substance mass, equaled the mass of his final products, even though there was a chemical reaction and what he started with isn't what he ended up with. So this is known as the law of conservation of mass. Now, when we do things in open air, we lose a lot of it to the environment. When these reactions are done, they are done in an isolated compartment that, insulated, so they can account for every single thing. We'll get to that. We deal with calorimeters, and one is known as a bomb calorimeter, and that's pressurized and it's sealed in, so you can account for every single mass. And that's when these are done. So when we do these reactions or look at reactions, out in the environment, we lose a lot of it, and you can't see it. It's not seen. So you don't understand that, what you're dealing with also ends up with the same mass as once you're done, meaning once the chemical reaction occurs. So if we know the mass, the beginning mass, and we seal this away in a container, then that means that once the substances react with each other in a sealed container, we will have the same mass, even if we don't have the same substances that we started with. So for instance, if we look at hydrogen, we have 4 grams of hydrogen and we have 32 grams of oxygen. That means that when we add these together, we end up with 36 grams of starting reactants, and that's a word that we haven't really used yet, but that's what reactants means, starting material in chemistry. And what's on the other end, so let me explain this real quickly if I haven't, and I don't think I have. This is our reactants, our substances that we begin with. So when you hear the term reactants, that means starting material. Then we have an arrow, and this arrow means that a reaction's occurred. Something has occurred. And then we have products on the other side, and products means what's happened after a chemical reaction. So if I start using these terms, these are what they mean. This is reactants, these are products. This arrow means equal. Well, I put equal for the mass. But this means something's been produced, something's occurred, a chemical reaction has occurred, things like that. In chemistry, I worked in an organic lab, and we tend to say yields. So something, there's different terms. Anyways, we know that if this isn't a sealed container, then we must have 36 grams of whatever we produced. And that's what's showing here. So I put this equal sign so you can see that whatever you have here has to equal on this side. So what does the law of conservation of mass mean? Mass, and this is a law, mass is neither created nor destroyed during a chemical or physical reaction. Again, that means the total mass of reactants is equal to the total mass of products. So if we look at an example here, we have 16 grams of methane. Methane is the gas that comes out of the stove. React with 64 grams of oxygen. It is combustible in the presence of oxygen. Fires don't start without oxygen. 36 grams of water are produced. So when you light your stove, you are actually having a chemical reaction because you're getting something, happening here. It's reacting with oxygen. 36 grams of water are produced. How many grams of carbon dioxide are produced in this reaction? So what you don't see that when we do a combustion reaction, which means that something has been combusted, and it's usually a fuel with oxygen, we produce carbon dioxide as the gas and water also as a gas, as a vapor. You don't see it, but it's there. So if we start out, so this is a good way to, I always write out reactions. So I determine where the starting materials are and I write them out. I do an arrow, and then if I know what the reactant products are, I write them out. I also pull out all the numbers and I write them directly underneath. And if I don't know what it is, I put a question mark, because sometimes when you're first starting to learn how to do chemistry, it's really hard to separate the information. It's a lot and it seems jumbled. So you have to learn how to break it down. I always suggest, and I still do it to this day, I write out everything and I write everything underneath. And as you start going into chemistry in further, 24A and B, more 24A, you will deal with a lot of reactions and breaking things down. So if you break this down, it makes it easy for you, so you can visually see what you're missing and what you have. So in this case, it's asking for how many grams of carbon dioxide are produced in this reaction. Produce, products. So if we add these together, we know what this one is. Then we can add this together. We can subtract this. We can see what the difference is in order to determine what is the amount that's missing, because whatever this total amount is here has to match this total amount on this side. So if we look here, that's where the 44.0 grams. So we can add this together. So I should have put 80 here, 80 grams. This is total of 80 grams. Add these together, you can see. So if there's 80 grams on this side, that means that there must be 80 grams on this side, but we're not given this one that's colored different. So how would you get that? Well, if there's 80 minus 36 gives us 44 grams. So whatever's on this side, you have to have on this side. And it's that simple. So suppose we burn 58 grams of butane in a lighter, it will react with 208 grams of oxygen to form 176 grams of carbon dioxide and 90 grams. This equals 266 grams. This equals 266 grams. So if you are missing one of these, on one side you should have the total, and then you can figure out what the missing piece is. All right, so now we're going to look at John Dalton. John Dalton was a school teacher, and in 1808 published a paper that helped define the framework for modern atomic theory. Dalton's atomic theory helped form the basis of our current atomic theory with some modifications. So we have since learned more information, and we modified from his postulates or his theories on breaking down what atoms were. But they were a strong foundation, and we just kind of built upon it. So understanding atomic theory. Let's go through this. Elements are made of tiny indivisible particles called atoms. The atoms of each element are unique. These things we've already covered. Atoms can join together in whole number ratios to form compounds. This means you will never get fractions. Everybody knows water's H2O. H means, and the 2 means there are 2 H's for every 1 oxygen. You will never get H 0.5 and O 1.75. There will always be whole numbers. H2O, which means 2 hydrogens, 1 oxygen, whole numbers. Atoms are unchanged in chemical reactions. This means that, in a sense, that let's say you have a dancing partner. You switch partners. You are still you after the change. You have just switched to a different dancing partner, but you're still whoever if you're John Dalton, you're still John Dalton by the time it's done. So let's see understanding atomic theory. So I copied this over again from what I just covered. So if we look at charcoal is actually carbon. Carbon's very interesting because it's diamond, it's graphite, it's carbon, mostly carbon, and it reacts with oxygen. So what this means here, this black ball means it's carbon. We have 2 oxygens, so this is where the 2 subscript goes. So these are our reactants, our starting materials, and it produces CO2, carbon dioxide. The di, which we'll start learning the names of this, but di means 2. So when we say it's carbon dioxide, oxide is oxygen. And you can see it's now here. So when I said dancing partners, so when a chemical reaction occurs, these oxygens are still oxygens on the other side. Carbon is still carbon on the other side. They have just now formed a different group. So where these were partners, now they're all 3 best friends. So that's what this means. One, we know that carbon atoms are different from oxygen atoms. That covers theory 1. 1 carbon atom combines with 2 oxygen atoms to produce 1 molecule of CO2. That's a whole number ratio. We have a ratio of 1 carbon for 2 oxygens. The C atom and the oxygen atoms are still there. They are still existing. They are not changed into something else. So the atoms themselves have not changed, even though a new substance has been created, which is CO2. So they have different properties. So carbon has its own properties, oxygen has its own properties, and CO2 has its own properties. So even though you are still dealing with the same elements, once it combines into a new compound, a molecule of CO2, that CO2 molecule has its own properties that are different from carbon and different from oxygen. So this is an example to explain these theories. And your book wants to point out 3 of the foundational ideas that are the most important. All matter is composed of atoms. The atoms of each element have unique characteristics and properties. That's very similar to what I just broke down. Carbon has its own properties and characteristics. Oxygen has its own properties and characteristics. And CO2, what has been produced from them. Carbon atoms still exist. Oxygen atoms still exist. However, now that they formed a new substance, which is CO2, CO2 has its own unique properties and characteristics. In chemical reactions, atoms are not changed, but combined in whole number ratios. That is 1 carbon for 2 oxygens. Those are whole numbers. We will deal with fractions in a sense when we're doing some calculations, but we will never end up with anything that's not a whole number. That's all I'm going to say. All right, so what do atoms look like? That's what they look like. I have seen something similar to this, and I'll be honest with you, in a physics class, I wasn't even sure what I was looking at. I was not impressed. So, to this day, I still wasn't sure if I actually saw an atom. So in the early 90s, scientists at IBM Labs were able to visualize atoms. I know I wasn't really impressed with this, but honestly, this is a very big deal because it's to this day, it's not easy to be able to, if you do Google, you can do searches and they'll show you different atoms that have been, you can see, but this is impressive because it took a long time and it is very difficult. And they were able to manipulate them to name IBM, which is, interesting. So they were able to move them around. They use a scanning tunnel, a technique called tunneling microscopy. I'm not sure what that is. All right, and scientists use X-ray crystallography. If you go into chemistry, you will deal with crystallography. Common technique for visualizing atoms is X-ray crystallography. Now, as you can see, what these balls that are colored, those are color coded specific for those elements. So it's like a fingerprint. That color goes with it's been assigned to those elements. So when we look at this, it's the same thing. We deal with certain colors, and they have been assigned. So when you see this, you see, I'm guessing just right offhand that these white ones are hydrogens, because that makes sense to me here, knowing what I'm looking at. So these colors are not just random to make them look pretty. They have been assigned a color for whatever atom that they're looking at. So in this technique, a solid is bombarded with a form of energy called X-rays. We will be covering X-rays in chapter 4. The patterns of the X-rays allow scientists to visualize the arrangements of atoms and solids. So basically what it is that these X-rays bombard the solid, and they can follow the pattern that is, so when they're hitting it and when they're not hitting it, and that creates, basically, I'm trying to explain this simplistically, like an outline. And because of that, then they can determine what the 3D arrangement is of all of this. So this is of aspirin. The properties of any substance depend on how atoms are arranged. The ability to see atomic arrangements through X-ray crystallography helps scientists to study diseases, develop new medicines, and design materials with unique properties. Why? Well, let me explain. This, you have to know how something looks. You know, if you're trying to fix a house, you cannot just randomly decide to, do something on a wall. You have to know what's in the inside. You have to know what it's made out of, where are the studs, and so forth. Is there asbestos? It's the same as knowing a compound. This is where a lot of companies spend a lot of money, because they need to know how a compound is arranged. Why? Because once we start getting into this, you'll start understanding that some of these atoms are bigger than others. And if you want something to come in, let's say right here, you can't. It's kind of very complicated. These things are sticking out, these arms, and you can't reach this one that you need. And that's where you have to start understanding how these are arranged, and what could repel it away, what could attract it. That's all of that. These, there's theoretical chemistry, and people study these to know what can be done to create something that can come in and attach itself, or so you don't want to spend money, tons and tons of money on something to try to get it to attack a certain compound, only for the thing to repel, or you can't even get it in because it's so big it's not going to come into here. So there's a lot of time spent on, people don't understand that there's a lot that goes into doing all this. I worked in an organic lab. I know I haven't really talked about myself, but I did 3 internships at Caltech, 2 in an organic lab and 1 in an inorganic. And then I ended up with a job through Caltech for 11 years until the pandemic. And I've learned a lot about how they spend doing a lot of this stuff.